Welcome. In this lecture, we will talk about speed, velocity, and acceleration, and then we'll talk about a special case known as free fall. Motion. An object is considered to be in motion when its position changes over time relative to a reference point. So as we've done many times before in previous lectures, we establish a reference frame. And this is important because motion can only be measured as relative to some stated point. So let's say that there is a person some distance away as measured by this reference frame. The person throws a ball. So all motion will be measured relative to this reference frame. We start a timer. This ball moves over time, and so we say the ball is in motion. Speed. Speed is simply the relative change in position divided by the amount of time traveled. Mathematically, it is written like this: V equals d over t. V is the symbol we use for speed, d is the symbol we use for distance, and t is the symbol we use for time. It's important to note that these are just symbols chosen to be used here. You can technically use any symbol to represent these values, but these are those that are commonly used. We will see shortly, however, that I will use a different symbol to represent distance or displacement when we talk about velocity. But returning to the case here, each of these quantities has an associated unit of measure. Distance is measured in meters, symbolized by m. Time is measured in seconds, and therefore speed is measured in meters per second. Speed is a scalar quantity, meaning it has only magnitude, not direction, so it is fully defined just by the value. If you look at your speedometer on your car and you see that it reads 60 miles per hour, for example, which is in a different unit system, but nonetheless it is in units of speed, that value of 60 is enough to fully define that quantity in that moment. Let's write a reference frame again. Let's say we have an object that starts at some horizontal position x sub I. This denotes the initial x position, and some position y sub I, which denotes the initial y position. And this object moves from the position that is shown here to some other position, to some final position in the x dimension, and some final position in the y dimension. This delta x here is the difference between the final and the initial positions, and the delta y is the difference between the final and the initial y positions. As we saw on the previous slide, speed is denoted as v equals d over t. Now in this particular case, we can write the speed in the x direction as v sub x, where the subscript x denotes we're looking at speed specifically in the x direction, is equal to the magnitude of the change in x divided by t. Similarly, the speed in the y direction can be denoted as the magnitude of the change of position in the y direction divided by the change in time. And again, as you can see, I've used these bars. Those bars indicate magnitude, which is the value you take. Essentially, it means you take the absolute value of whatever that difference is. Velocity. Velocity is speed in a given direction. It is the state of motion of a system. So notice that I say speed in a given direction. So now we have a value. Speed, remember, is a value in a given direction. So now we're going to have a vector quantity. And so the notation will change a little bit. Notice that now boldface is used. V is now no longer italicized. It is boldface because this is the notation I use to indicate a vector quantity. So velocity is a vector quantity. So V is velocity. This is our distance. More technically, you could say it's the displacement, but we will not be discussing the difference between distance and displacement in this class. And this is your change in time. Now, in the previous definition where we talked about speed, instead of putting delta time, I just put time. This delta t is actually more specific and more clear notation than what was given for the definition of speed, but again, the same thing is meant. You have some change in distance, vector change or displacement, over some change in time, the time interval which you made some sort of change in position. So velocity is just the change in that position divided by the change in time. And as before, distance is measured in meters, time is measured in seconds, velocity is measured in meters per second. So the units are the same as they were for speed. The only difference is that velocity is a vector quantity, meaning it has magnitude and direction. Practically, how does that play out? Well, if I have this car, let's say this car is going in a perfectly circular path. And let's say you're driving this car on this perfectly circular path. And you look at your speedometer and it's reading 40 miles per hour at every point along the path. So you're going at the same speed along the circular path. So the car has a constant speed, but the velocity is changing. And why is that? Well, if you're going in a circle, it means that your direction is constantly changing. So even though your speed is the same, the velocity, which is a vector, meaning it has direction, is changing at every point along the path. So we say velocity is changing here because the direction is changing, even though speed remains constant. And that leads us to the next term that we will define. Acceleration. It's simply the change in the velocity. It is the change in the state of motion of a system. It is simply written like this. Acceleration, which is a vector, is the change in the velocity divided by the time over which that change in velocity occurred. So a is our acceleration, delta v is our change in velocity, and delta t is our change in time. And the units, of course, the change in velocity is measured in meters per second, the change in time is measured in seconds, and therefore our acceleration has the units of meters per second squared. Of course, this is all in the system of international units, which is the system we use for this course. Even though my examples may be in other units as I'm talking, the units we will mostly be using for problems in this course will be the SI unit. Again, acceleration is a vector quantity, meaning it has magnitude and direction. So let's look at some examples of this. This is an example of acceleration. You are speeding up, so your speed is changing. If your speed is changing, obviously your velocity is changing, and acceleration is defined as a change in velocity. If you slow down, your speed is changing. Again, if your speed is changing, it means your velocity is changing, because velocity is just directed speed, so speed with direction. If your velocity is changing, you're experiencing acceleration. If you turn, you're changing direction. If you're changing direction, it means you're changing your velocity, because velocity is a vector, which means it has direction. So if you change the direction, you're changing that velocity, and by definition, acceleration is the change in velocity. All of these are examples of changing velocity, and therefore all of them are examples of acceleration. This is speeding up, where your velocity and acceleration are in the same direction. These are vectors, so we illustrate them with arrows, as we have before with vectors. If we slow down, our velocity is still forward. We're still moving forward, so that is our state of motion, but our change in the state of motion is opposed to that. It is to the left. Or if we turn, our acceleration is down, our velocity is at some angle. Talk about free fall. Free fall is a specific scenario in which an object's change of motion is dictated purely by gravitation. What does that mean? It means there's no air resistance, no friction, nothing else. No, I'm not pushing on something, I'm not pulling on something. An object is completely falling in a vacuum under only the influence of gravity. Gravitational acceleration is represented by this lowercase g, and it's 9.8, roughly at least, 9.8 meters per second squared. In the textbook Conceptual Physics, which is the textbook these lectures are following, it is approximated to 10 meters per second squared. So if I have my reference frame again, the vector version of g is this negative of the g value in the y-hat direction. So it's saying that the vector g is pointed down with a value of roughly 10 meters per second squared vertically. So vertically downward. Let's do an example. We have a ball and it's at some initial height, some initial y position relative to our reference frame. It has some initial speed in the y direction, and it's actually the velocity because it's pointed downward. I simply haven't used vector notation here because we're only concerning ourselves with one dimension, and if we concern ourselves with one dimension, we can kind of hand wave away the need for the vector notation. But you could write a boldface here and say, oh, this is a vector pointed down, because it truly is. And the ball is experiencing some acceleration in the y direction, which is our negative g, as we saw on the previous slide. And it's negative, again, because we've indicated that upward, based on our reference frame, is positive, therefore downward is negative. So sometime later, because this ball is falling, we're at some new vertical position, y sub f, so our final y position, let's say, and we're moving with a new velocity, or new speed in the y direction of v sub y sub f. Lots of subscripts here. Try not to get lost with the subscripts. And at this new position, our acceleration is the same. The acceleration does not change, but the speed or the velocity is changing, as indicated by the size of the arrows. Because remember, acceleration is the change in velocity. So we have a constant change in velocity. That means we have a constant acceleration. So what is the equation that we use to describe this? Well, if we want to know the final position, if we are given the initial position, the initial speed, and the initial acceleration, assuming the acceleration remains constant, well, what do? Well, we know the final position is going to be related to the initial position, but this equation doesn't make sense because we know that the initial and final positions are not the same. So this equation is incomplete. We need something else. I can't simply just add velocity because they're different units. I can't take a velocity or a speed and add that to a position. You can't add meters to meters per second. That does not make sense. So I have to multiply this speed by time. But that's still not it because we know that the velocity is not constant throughout the motion. I must add another piece. Now this equation is not explicitly in the textbook, Conceptual Physics, but it will lead us to a very simplified equation that is in the textbook. So hold on and we'll get to the simple equation that is in the textbook. But if we start from this equation, we must remember that based on our reference frame, downward is negative, so we will now put negative signs for all the values that should be negative. And let's subtract yi from both sides. And I'm doing that for a very specific reason, because the change in the y position is really just the height, or the change in height. And I will denote that by h. And we're having a negative change in height because we're going from some high position to some lower position. So the change in the y position is simply the height. And we know that if we want to get to the simplified equation as found in the textbook, we have to make the simplifying assumption that we took this ball and we didn't throw it down to the ground. We just held it and then dropped it from rest. So it started with initial speed of 0. So that term goes away. So this is when we assume the object is dropped as opposed to thrown down. And now we have a negative on both sides. We had that already. We multiply both sides by -1 and we get this equation. This is the textbook equation. This equation that I began with up here is a more general equation that you will not find in your textbook, but it may be useful to use this if you can understand how to use it. However, for the purposes of this course, you only need to use the textbook equation. This was an example for vertical motion. Let's look at an example for horizontal motion. We start with the same reference frame. We have a ball, some initial x position, some initial speed in the x direction. Acceleration is downward, so it doesn't really affect the motion. And let's say sometime later, we're at a new position, x sub f, so a new final position, x sub f, with a speed of vx sub f. Of course, the acceleration is still the same here, but notice that the acceleration is completely perpendicular to the direction of the ball's motion. What equation do we start with here? Well, we want to know what the final horizontal position is if we know the initial position and the initial speed and the acceleration. So the final position, again, just as before, can't simply be equal to the initial position, because we even see here, it doesn't make sense for the final position to be equal to the initial position. If I roll a ball on a flat surface, it starts with some initial speed. So where it ends up is not going to be where it started, if nothing else is interfering with it. So we must add to it some piece of this, some initial speed, but we have to multiply it by time to get the proper units. And there's a deeper reason why this works. This comes from Newton's second law and taking some integrals, which is related to calculus, if you're familiar with that. And we add acceleration. This is all from Newton's second law, which we haven't talked about yet in this course, but we will. Now, horizontal motion, in the case I've outlined here, has no acceleration. The acceleration you do see in the picture is downward, but that does not contribute to any change in horizontal motion. So there's no acceleration in the x direction. There's only acceleration in the y direction. So we can safely remove it from this equation. There's no a sub x, and so we say that's 0. Again, we're doing this because we want to make simplifying assumptions to get the equations shown in the textbook. So this leads us to then saying that the initial speed is the final speed, because if there's no acceleration, there's no change in velocity, no change in speed. And so we're just going to simplify the notation and write this as v. So we rewrite this, we subtract xi to both sides, and we know that the change in the x position is the same as writing the distance. So the distance traveled equals v times t, and this is the textbook equation, whereas the other equation up here is the more general equation. Now let's do some examples under the heading of linear motion. So car starts at rest and speeds up to 26.8 meters per second in 3 seconds. What is the value of its acceleration? Well, we need to write down the givens. It starts at rest, so we know the initial speed is 0 meters per second. We know its final speed is 26.8 meters per second. And we know the time interval taken to change from 0 to 26.8 meters per second is given as 3 seconds. So what is the acceleration? Well, this is a simple plug and chug problem. We use our definition of acceleration, a equals delta v over delta t, where we're not really caring to write the vector notation here, because all we care about is the value. We don't care about any direction. And we write vf minus vi, because that is what delta v is, and we plug in our values. 26.8 meters per second minus 0 meters per second, all over 3 seconds. And this yields a value of 8.93 meters per second squared. Problem number 2. A Camaro accelerates at a rate of 5 meters per second squared for 3 seconds. What is its change in velocity? Again, we look at the givens. We're given an acceleration of 5.0 meters per second squared. The time interval is 3 seconds, and our delta v is unknown. Once again, we start with our definition of acceleration. A equals delta v over delta t. Now, we need to multiply both sides by delta t because our goal is to isolate delta v. Now we have delta v isolated on the right-hand side, but conventionally we put it on the left-hand side. So we simply switch that around, and then we plug in our values for a and for delta t, multiply that out, and get a value of 15 meters per second. Problem number 3. A dart leaves the barrel of a blowgun at speed v. The length of the barrel is L. Assume the acceleration is uniform throughout the barrel. Find the time interval, delta t, the dart takes to escape the blowgun. Now you'll notice something different about this problem. The givens are not given as values, they're given as symbols. So speed v and the length of the barrel L, those are considered to be given quantities, even though specific values are not assigned to them. We want to find delta t. So let's draw a picture first. Here is our blowgun, which I guess here it just looks like some pipes. Here's our dart. We want to set up a reference frame, and let's start writing some of our givens down. We assume that it starts at rest, the dart starts at rest inside the blowgun, so our initial speed is 0. The dart races through the blowgun, comes out the other side, travels a distance, delta x equals L. Remember, L is our given, and when it exits with a final speed of v. So we put those in the given category, and we note down that the time interval is what we are looking for. So what equation should we use? Well, we should consider an equation that we saw in a different context, this is the one we saw in free fall. We can't use this exactly as it's written, because it's written specifically for free fall, but the concepts can be used. We notice that we have an h, which is just our distance. We have a g, which is a constant acceleration, and we have a t, which is a time interval. Now h is usually saved for when we're dealing with heights or vertical displacements. Here we're dealing with horizontal displacements. Now we could use h because it doesn't really matter what symbol is used, but it's probably safer to not use h just to avoid confusion. The symbol g is often reserved for gravitational acceleration. So again, we could use it as our constant acceleration symbol here, but it's best not to. Time interval t, we could leave it as t, or we can use a delta t, depending on what you prefer. The way that I will rewrite this to fit our specific scenario is as follows. Delta x equals 1/2 a times delta t squared, where delta x is the distance, a is our acceleration, and delta t is our time interval. So I wrote it like this just because it seems to be a little bit easier to keep track of, because we're dealing with horizontal motion now, as opposed to the equation which was given for vertical motion, but the concepts are exactly the same. Distance is still distance, acceleration is still acceleration, time interval is still time interval. This is an example where you see that notation is just flexible. The important thing is you understand what the notation means. What does each symbol represent? Which physical quantity does each symbol represent? And then you can write pretty much whatever you want. The things that you have to keep the same are what are given. So what's given? Well, delta x is given. A is not given. and delta t is not given. So let's replace delta x with our given quantity, which in this case is simply a symbol to represent the length, because that's the total distance the dart travels. Now we have a problem because we have one equation and yet we have two unknowns. This cannot be solved. We have to introduce another equation. So let's look at things that are not given. A is not given, so we don't know the acceleration. We are only told that it's a constant acceleration. And we don't particularly care about the acceleration. The problem asks us to find the time interval. So we probably need to write an equation that has acceleration in it, a different equation that has acceleration in it. So let's write simply the definition of the acceleration. And the delta v is simply the final minus the initial. So let's put that in. And look at that. We have vf and we have vi, both listed in our givens. So we can replace the vf and vi in the acceleration equation with the given quantities. So we have v minus 0 over delta t. Now 0, we don't need to put that there. It doesn't matter. It's not doing anything. So we rewrite this as a equals v over delta t. So now we have two equations. What we should do here is we should substitute the second equation into the first equation. So we take our a from the second equation and we plug it into a in the first equation. That way we no longer actually have a remaining. And I'll show you what that means. Throw that in there. And now our a, which is v over delta t, is at least partially given. I think what I put there as given is not fully true because we don't know delta t yet, but we have v. And these delta t's actually cancel out. At least this one on the denominator cancels with one of the delta t's in the numerator. And that leaves us with this. So let's move that over. And what are we trying to find? We want to find delta t. That's the whole point. That's the unknown. At least the unknown that we care to find. So let's rearrange this a little bit. Let's multiply both sides by 2 over v so that we can cancel out the v over 2 on the right hand side, and we're left with 2l over v equals delta t. So we've isolated delta t, but again, by convention, we tend to put the isolated variable on the left hand side, and we do that here, and we have our answer. So this is the answer. Delta t is written in terms of our givens. L is a given quantity, and v is a given quantity, at least in this example. So we are done. In summary, we discussed speed. Speed is the change in distance over the change in time, and it's just a value. There's no direction associated with speed. It's a scalar quantity. We discussed velocity, which is directed speed. It is a vector quantity, so it requires both magnitude or value and direction to be fully defined. And acceleration is the change in the velocity. And we talked about free fall, which is a scenario where the only thing influencing the motion of a system or an object is gravity. And I'll see you next time.